Very nice to see so many people here today. New faces, very exciting. My name is Malte. I'm 25 years old and I graduated from NTNU last summer. And today I work as a software consultant at Knowit. So I'm interested in artificial intelligence and machine learning. So for my thesis, I made a system that was able to generate poetry from images as input. And I'm going to share my experiences with you here today. As I said, it was a master's thesis done in the spring of 2017. The title was Computational Linguistic Creativity, Poetry Generation Given Visual Input. Yeah, and it just got accepted into the 9th International Conference on Computational Creativity. So I'm going to Spain in 2 weeks to hold this, or some other variation of this in Spain in 2 weeks. Yeah. First, I'm going to talk a little bit about what poetry is before we talk about neural networks, the data set, architecture, some results, and the observations I made while doing this. So what is poetry? A lot of different people has defined poetry in a lot of different ways. So in my definition, I made it very precise so it was clear what I was going to generate. Basically, I define poetry as any text that can hold any amount of lines, where all the lines must contain the same amount of syllables, and a line must rhyme with another line. The way you can evaluate your poetry is by these 3 metrics made by Manorum in his PhD. It's grammaticality, poeticness, and meaningfulness. Grammaticality is in which way the poem is grammatically correct. The poeticness is how well it rhymes and how well the flow of the poem is, while the meaningfulness describes in what degree the poem conveys a message. Yeah, neural networks. Neural networks are computer models that are based on the human brain. They consist of neurons, the circles here, and the links, which are the arrows. The neurons are grouped into layers, and there's always one input layer and one output layer, but there can be any amount of hidden layers. The input of the data goes into the input layer, and then results come out at the output layer. The size of the input layer represents the number of features you're looking at in your data. So for instance, if you're looking at a picture or an image, it's often all the pixels of the image. And if you're looking at some data set of cars, let's say you look at the color and weight, then you have 2 input neurons, right, for each of those features. The size of the output layer represents how many classes you're trying to predict or classify. So in this one, there's 2 classes. Maybe you're trying to figure out in your image if it consists or if it contains a monkey and a seat. Right, then each of those represents those features. They're able to learn very complex behaviors, such as image recognition and natural language processing, and often they're often used for classifying and predicting certain things. The way you train them. It's a 3-step process. The first thing you do is just initialize it, where everything is just randomly, or depending on what kind of initializing you use, but often random is used. The first thing you do is to feed the network data. So you feed it through the input layer, and it's something, and you get some numbers out at the output. Then you can kind of measure how wrong the output were. In the start, it's going to be not so good results. But then you can measure how wrong you are, and then you can go backwards into the layer and update the weights and parameters of the neural network. So the next time you put in the same input, it's going to be slightly more correct. And when you have a finished trained model, you just simply feed it the new data you want to experiment with. And hopefully something decent is going to come out at the output layer. This is a feed for neural network, very vanilla type. So what has come up in research in recent years is convolutional neural networks, which has the exact same ideas as the vanilla neural network, but we introduce convolution and pooling in addition to that. So as we can see in this image here, convolution, you can think of it as you make a square that loops over this square here, and it loops over the image starting at the top left corner, and then it looks for features that are present in the picture. So when it loops over and it's right here, it's probably going to figure out that, oh, there's a boat in this image. And then you take it deeper and deeper into, and then it outputs, oh, there's probably a boat here. And convolution is good for 2D input, and images are 2D input. So that's why it's often used for that. And I used convolutional neural network in my thesis and recurrent neural networks, which I'm going to talk about now. So with recurrent neural networks, you have the same ideas as a vanilla neural network, but it has added some memory. So instead of just taking input by the previous layer in the network, it also has a hidden state inside, so that for every time step you have two inputs into the neuron. One here and the hidden state it has, so that it always remembers where it is. And it's really good to use in sequential data. So for instance, it knows in a sentence, it always knows what words it's on. So it remembers all the previous words. Yeah, that's the background you need to know about this. Yeah, and then the architecture of my system. If we start at the top right here at the input image, I classified the image using a convolutional neural network. And then start with an image, and then now I have an object in the image. Let's say we have the boat. So now here I have the boat word. Then I find related words to the boat, and here we have a bunch of related words, maybe sea, water, whatever. And then I find rhyming pairs that I'm going to use in my poem, so that the poem rhymes. And then I'm going to use this. This is one input. So I have rhyme pairs and related words from this branch here on the left side with the image. And then on the right side, I have a data set, and then I pre-process it a little bit. Then I train my LSTM network. LSTM is just a form of recurrent neural network. Then I use this train model to predict what word should be in my poem. And then I have a little bit of cheating at the end. Yeah, so the data set I used. The data set, I used Python and Beautiful Soup to scrape lyric databases online. I can't distribute it because it's copywritten by the artists. When I was done scraping, I had 206,000 songs with 46 million words and a vocabulary of almost 400,000 words. The vocabulary is the amount of unique words you have in your data set. But I don't know. But I don't think that does English even have 400,000 unique words? I don't know. So I kind of thought that a lot of these words are probably not English. So what I did was I looked at the language, and I removed everything that wasn't English. For that, I used NLTK, which is really simple. You can check if a word there is English or not, and then I just and then if a song didn't contain 95% English words, I just discarded the song. There was also a lot of escape characters because I just scraped websites, right? So there's a lot of junk escape characters. I had to use regular expressions for that. Also a lot of custom-made messages, such as thank you, Malte 111, for submitting this song to the lyrics database. So I had to remove those two. It was a lot of manually looking and regular expressions. Also, there's a lot of verse and chorus notation, such as at the start of every verse or chorus, it often starts with this is verse 4, this is the chorus, verse 5, and so on. So I had to remove those as well. And then when there is multiple artists singing, let's say Rihanna and Eminem are singing together in a song, it's often says Eminem is singing this part, Rihanna is singing this part, and so on. So I have to kind of remove the name of the artist. However, it didn't really work out because a lot of rappers and wannabe hotshots, no, just kidding, they often say their name in the start of their song, so I can't just remove the artist name. Also, there's a lot of notation of physical movements. Which means, like, if Elvis is singing a song, it's often like Elvis runs to the left, and then he sings this, and then he runs to the right and sings this. So I have to remove those two, and that's regular expressions as well, kind of. It's hard. There's still the trails of these in the data set. You can't remove it all, but I think it was sufficient enough, what I did. When I did all of that, I had 80,000 songs left and a vocabulary of 91,000, which is a bit of a problem. There's two reasons for this is too big. There's two reasons for that. One reason is that the output layer, if there's 91,000 words, the neural network has to try to predict. The output layer has to be 91,000 in size, right? And it's going to take forever to train if it's that big. I tried and never finished a single run. Second of all, it's not feasible to expect the neural network to be able to predict 90,000 words. Let's say the word is only in the data set one time. Then how is the neural network ever going to learn to predict that word? It's just not possible. So these are the words I'm going to, from now on, call zero prediction words, because they're there so rarely that the neural network never learns to predict them. However, you can't make the vocabulary too small either, because then you're going to have no words to make your poem with, right? One way of looking at this is to so if you remember the architecture figure, you had that there's kind of two branches that meet in the middle, and the neural network, my LSTM neural network, has to kind of cover words that are found on the other branch. So what I did was that I just in this figure, I took 5 pictures, and I saw with this size of vocabulary, it's going to cover this percentage of songs. So I took a zebra picture, I found the related words, say it 100 related words or something, and then in a vocabulary of 15,000 of the most frequent words in the data set, it was able to cover 30%. So then from here, I saw that 30,000 in size of vocabulary is probably fine. Just why not? Yeah. And then I ended up with these 3 data sets here. And at the very end, I just used data set 2, which is going to be the data set from now on. Yes, so the image recognition part, I just used the Google's Inception. I don't know if anyone here has heard of it. It's a convolutional neural network that is pre-trained on the ImageNet large-scale visual recognition competition. And it was, at the time, in 2016, 2017, one of the best performance convolutional neural networks. It's, for anyone who wants to try it, it's really easy. You can just go to the URL down here, and you can just get the neural network yourself and play around with it. Also, the source code is there too. So after I can identify what's in an image, I have to find related words and the rhyme words. The related words I found by using ConceptNet, which pretty much just looked like this. Let's say I have found out that there's a car in my image. Then you just ask ConceptNet what are the related words, and they're just going to give you a bunch of words or like phrases sometimes. And then you have a lot of related words. For the rhyme words, I used CMUdict and Python. What you do is that you feed CMUdict a word, and it comes out like this. This word is dictionary. It's going to look like this. You remove all the numbers, because those are the stress syllables. They don't matter. But we just want to check if it rhymes. So at the very end, if it rhymes with another word, you can use some rhyming rules for that. I'm not going to cover them here. Yes. So the training of the LSTM network. The LSTM network is used to predict the next word in the poem. I used Python and TensorFlow. A lot of pre-processing steps are still need to be made. Even the pre-processing that I did earlier, you still need to do more. You need to do all of the mentioned here. I'm not going to go into it here in detail. And when you have, so now you have the rhyming words, you have the rhyme words, you have the rhyming words, and you have the related words. So now you can kind of make a search algorithm that tries to find the next word in the sentence. So what you do, or what I did, was that I started at a root state, which is just a completely empty poem. Then I used the neural network to try to predict the top. What I did was to predict the top 30 words that are going to be next, based on the image and some other parameters. Then for each of these 30 words, I take the 30 next words, right? And then these ones are going to have values. The arrows are going to have values connected to them, so that this plus this, word 0.1 plus word 1.1 is then be the score after two words, right? This is going to be score X, and then the word 0.1, word 1.2 is going to be score Y, and so on. And then I could kind of score how good each sentence is. However, there's a problem, because the tree is going to get very big, and you run out of memory, and it's going to take forever to search. So you have to use some pruning. So based on this score that I have for each sentence, if the score for some branch is not high enough, I just skip it. Yes. And then to the experiments. I did 3 experiments. 1 was training the neural network, and 2 was connected to the poetry. Yes, we're going to go through it. The neural network I trained on a GTX 970, my brother's stationary computer. He was not happy. Whoops. It took 34 hours and 41 minutes. I reached a word perplexity on 36.7. Word perplexity is kind of a measure of how confused your network is. So a lower score is better, because then your network is less confused. I reached a really good word perplexity, while Saremba reached 68.7. However, it's not that great as it sounds, because In song lyrics, there's a lot of repetition. The same words get often repeated together. Words just get repeated all the time. And therefore, the neural network is kind of, well, if I just get that word, guess that words many times, then we're not going to be doing so poorly on the word perplexity part. Also, if you guys remember the 0 prediction words, where the words are never, that are maybe mentioned once or twice, they never get predicted. So in the bigger vocabulary of 27,000, the 30,000 one I chose, it doesn't get so confused because it knows exactly which ones it's going to guess. But when you reduce the vocabulary a lot, then we're removing all of the infrequent words, and now only the frequent words are left, and then it gets a lot more confused. And then I got 247 word perplexity. And then to the poetry. I generated 153 poems, or stanzas as they're called. 46 people in total were included in this. These are the scores. The scores goes from 1 to 3. 1 is the worst and 3 is the best. In poeticness, grammaticality, and meaningfulness. There's the average on the top row, the standard deviation in the middle, and the median on the bottom row. That was one of the poetry experiments. The other one was that I asked some people to, I gave them the image, and then I asked some people to write a poem for me on the exact same format as my system generated it. And then I asked the participants in the survey if they could tell the difference, which one is the human-generated poem and which one is the system-generated one. So I'm just going to read them up. There are four pictures, or 4 picture-poem combinations that I'm just going to read them so you can get how the flow is supposed to be. And then you can see for yourself if you can guess which one is the system-generated one and which one is the human-generated one. It's been a long time and I've bees, but I don't know what to get disease. I'm all out of love, oh so sweet. Just give me one more chance to meet. I'm flying in the warm air. The other bees are very fair. It is a beautiful Sunday. I'm leaving later today. And the other ones. I want to see swans in the sky. You and me, we're in for fly. If there's a lake out there for goose, there's no limit for excuse. Eating dinner like a wild goose. Food is something that I can't lose. Although cooking is really tough, nothing better can make me bluff. Broomstick on the back of my broom. Move on like dead man can assume. I don't know what to do and sweep. It makes me think that I'm asleep. Checking the status of my broom. I need the broom to sweep the room. I have no choice to keep waiting. It's hard for me to stop hating. And the last one. It's been a long time since the kick. It makes me want to hold you stick. And I know communication. I've got so much combination. Tapping on my keyboard at night, hoping it will not cause a fight. You are my only listener. Don't let me be your prisoner. So, in all of these ones, four images here, all of the bottom ones were generated by humans. Yes, humans. So all the top ones was from my system, and the bottom ones was from humans. People could tell it in 76.5% of the time. Yes. I did not give them in that order when I asked them, but it was just to simplify stuff, I made it like this here. Yeah.
Did you ask 46? Did you ask 46 people or?
Yes.
Okay.
38. No, 38 here. 38 people in this one and 46 people on the the grammaticality, poeticness, meaningfulness one, yes. Yes, those numbers add up. Some observations I made. Yes, in song lyrics, there's an extensive use of I. Yeah, you can just read the poems on the other side here. It's just a bunch of my results. There's an extensive use of I, or a form of I, such as I am. Let's see what's in this one. I'm and I, only in this one. Yeah, extensive use of I. I think it was in 87% of the poems, I is in there. There's a lot of repetition. So what I did was that when you were to predict the next word, what the LSTM did, I also said that, okay, if this word has already been in the poem, I'm going to get it a slightly worse score, so that it's not just going to be I all the way. There's also a lot of love and related terms to love, which also can kind of see throughout the poems. And there's also a lot of zero prediction words that just occur once or twice. And I also want to say that the grammar this makes is a lot better than what I thought when I started. I'm doing a little bit of post-processing and fixing a little bit of grammar, but it is not a lot. And all of this is basically just predicted by the network itself. Yeah, I'm just see, these are pictures I got in, and these are the system-generated poetry that got out. And here you can see the score. It's a vector. It's the great. Now I can't remember in which order they come. Meaningfulness at the end, and then grammaticality first. So poeticness in the middle. So grammaticality, poeticness, meaningfulness. Yes, that's the order of the score. Yeah, I can also do any questions now if you guys have it. Any? Yeah.
Yeah, so I think all of these are in the pattern of AABB.
Yes, only AABB.
Did you try something else?
No.
No.
I was thinking, yeah. I was thinking about it, but I just chose AABB. There was a lot of other stuff to do as well. Yeah.
So you said that you cannot publish your dataset because it's copyrighted, but can you publish your trained model or your network?
I actually got a question of that on the Kielferja. But this is, I have checked that these ones, those lines here are not in the data set. So these are not copied from the data set, and I checked it out a little bit. I asked my supervisor about it, and he said it was probably okay. And I also didn't find anything that said otherwise. So, yeah, sure.
Why did you not use a hard cutoff to remove the zero prediction words? I figure you could just remove every word that is not used more than, let's say, 10, 100 times.
Yeah, you could do that, definitely. I didn't try it. Yeah, but that's another way of doing it for sure. The thing, now I haven't done it, so I don't know, but maybe you're gonna cut a lot of words if you do that, maybe too many. Because even, okay, so when I say that the network can never predict anything that's only there once or twice, it's gonna predict it sometimes. And it makes it a little bit more interesting if you have more words there. But yeah, it's definitely a thing you could do. And in this system, there's a lot of future work you can do. And you can, instead of using an image as input, you can use music, for instance. That would be really cool to see. make poems out of music, for instance. Or you can try to cut up the zero prediction words, or you can do a lot of cool stuff. Yeah, definitely.
What was your strategy for selecting images?
So in the survey, the participants just gave me images they chose themselves. Yeah. So I gave them a link to Flickr, and so I knew that they had this copyright, so I could use them in my thesis. And then I just told them to give me any picture you want. Yeah. Preferably with something that Inception could identify, because it's trained on 1,000 classes. So if you give me something that's out of that, it's not gonna be able to see what's in the image, right? But if you give me something that's inside of there, it's pretty well. I also told people to take the pictures themselves and give it to me. There are some examples here. Yeah, which also turned out great, or good enough, depending on how you see it.
Did you try your model without the inception part? So instead of having users feed you an image, they could just feed you 2 or 3 words, maybe unrelated, and then create a poem, which might be harder since you're basing it on 2 words that are not related.
Yeah. Yes, I tried that a lot, especially when I was debugging and stuff, just to feed it words that were just unrelated and stuff. I only did it myself, so I only saw the results, but it just fun, weird stuff happened. And yeah, I never did any survey about it, no. I don't know how many more are left. I think there's one more slide left after this. I hear people have taken their own pictures and sent me. Yeah. Yes. So, can a machine become the next Shakespeare? I think definitely yes. My system cannot. But in the future, for sure, I think the only question is when it's going to happen. Yes. Okay. That's it.